Welcome to the next lecture on casting. Till now, we have gone through the fundamentals, and in this lecture also we will keep continuing with the fundamentals. Plus, we will also try to understand different parts which are involved in casting and their design considerations. For example, sprue, design of a sprue, riser, design of a riser. So, these are some of the things we will start doing it, and I am sure you would have done the 3 exercise which I have given to you in the last lecture. End of the lecture I gave you 3 assignments, right. Please try to do it. So, when you do it, you will start appreciating and understanding all these things, and when you do a fluid flow through a pipe, you have to keep continuity equation into mind. So, A1 V1 equal to A2 V2. So, keep that formula in mind, and then when you design for whatever I said L by D, so you should have that in mind and then plan it. In this lecture, we will try to see sprue design, riser design, more information about casting, sand casting, then mold design, and finally, we will try to have a recap. Let us first try to understand sprue design. As you know, when I try to pour a liquid into the sand casting to go towards the mold, I pour the hot liquid into a funnel. So, this funnel is called as sprue. It has a wide opening which is called as pouring basin. From the pouring basin, the hot liquid will flow down towards the mold. So, this portion is called the sprue. The down sprue is the delivery tube by which the hot metal or the metal travels from the pouring basin to the bottommost part of the casting. So, you can have, if you have a mold, you can try to have the sprue here up, or you can try to have the sprue here, right. So, both are possible, but here we are trying to talk about a down sprue. So, from the pouring basin to the bottommost part of the casting, a falling stream will reduce in cross section. Why? Because of the continuity equation. A falling stream will reduce in cross section area as it falls. As it falls means as it moves down, due to a combination of surface tension and velocity increase from the acceleration due to gravity, right. And then this phenomena is called as vena contracta. The shape of the down sprue is in a well rigged system must be tapered from top to bottom with the large area on the top. This is to ensure that the stream is enclosed by the mold at all times and the air is excluded, because finally mold is like a box. The box is filled with air. As and when a liquid enters, the air should go out. This is to ensure that the stream is enclosed by the mold at all times and air is excluded. A parallel or a negative taper. This is a positive taper. This is a negative taper. You can also have parallel tube. This is what I have given the exercise for you. A parallel or a negative taper down sprue creates regions of low pressure, and the melt stream can behave like a venturi pump. So, if it is like this or like this, it can behave like a venturi pump. So, we always will have the sprue. In fact, if you try to solve the equation and see, you should have a sprue like this. So, a sprue of this kind is the best, but manufacturing with this exponential curve is difficult. So, we always prefer to have a taper one. Why is the sprue tapered shape? Reason, the sprue is needed to guide molten metal into the mold cavity during casting. So, it serves as the entry point for the metal and ensures a proper flow. It avoids air pockets. It ensures uniform filling. So, you see here, if it is not tapered, you will have like this. Then you will have aspirations which are getting the air which is getting into if it is parallel, right. So, that is why we always keep it as a taper. It helps the flow control. It prevents turbulence and splashing. It also aids in maintaining smooth metal flow. It minimizes the risk of metal freezing or solidifying prematurely. So, for all these things, you need to have a taper. Is that clear? If you have a parallel one, the air can go inside and then it can go fill here. So, the solidification will happen. Slowly, this will get closed. So, if the distance is long, at some point of time the taper will get, the both sides will meet and you will have a shut of the flow happening. So, that is why we always try to keep the sprue taper. Now, let us look into the riser. It is used in sand casting mold to feed liquid metal to the casting during freezing to compensate for solidification shrinkage. The riser must remain molten until after the casting solidifies. The Chiourne's rule can be used to compute the size of the riser that will satisfy the requirement V by A ratio. See, if it is a straightforward cylinder, V by A is good. But if you have a complex shape, then this becomes little difficult. The riser represents waste metal that will be separated from the casting part and remelted to make subsequent casting. What we are trying to say is, suppose let us assume you have a part like this and then you have a riser which is attached. The metal flows through the riser also, right. So, what we are saying is, once the part is solidified, so what we do is we trim it here. Now, this portion will be remelted and we will again use it for filling the mold. So, it is considered as a scrap which can be reused. So, the riser represents waste metal that will be separated from the casting part and remelted to make subsequent casting. It is desirable for the volume of the metal in the riser to be a minimum, because anyhow you are going to cut it. So, though you say you are recycling it, but still it needs energy to first of all cut it and then you have to melt it. So, it all takes energy. So, that is why what we do is we always try to keep this volume as low as possible. So, V by A. So, we try to keep the V as minimum as possible, but friends, keep it in mind, once the volume goes low, the area goes high, then the solidification happens. So, you have to hit a trade off. The riser geometry is normally selected to maximize V by A ratio, which tends to reduce the riser volume as much as possible. The riser can be top riser or it can be side riser or a blind riser. The riser can be designed in different forms. One is side riser, the other one is top riser. The side riser, it is attached to the side of the casting through a small channel. The top riser, it is connected to the top surface of the casting. There are two types. One is called as open type or open riser. The other one is called as a blind riser. The open riser, it is outside at the top of the casting. This is what is generally preferred. We can also have blind risers, but it is very difficult for us to have a control on the surface and quality of the product, but it is followed in a large extent moment you have optimized the process. It is entirely enclosed within the mold. So, you see here the mold. So, this fellow sits inside the mold and it fills here, then it fills here and then it starts feeding here. So, blind risers are good. Why? Because here you have heat extraction which happens, here it does not happen, it is good, but fabricating it is difficult. So, we always prefer to have top risers or open risers. So, when we talk about sand casting, so sand casting, as I told you, will be made of two parts. Okay. The A portion talks about the top view, and the front view is seen in the B figure. Okay. So, what we do is, we will see here very clearly the pouring basin, and then it has a taper. So, that taper is seen here. Then it is attached to a runner which goes here. Okay. Then it is fed into a gate, okay, this gate, and then it is going into a mold. So, you can see here mold, you can see here mold. So, now when I see the on top of the mold, what do I see? I see is the riser, and then I see the mold, and there is a core. This core is used to give us the internal geometry. So, top view, front view. So, front view, you can see here there is a parting line which divides top and bottom, which is cope and drag. The cope and drag are attached, because they should not move. They are attached by using a pin, a lug and a pin. Okay. So, this entire dot black portion is the sand. So, here the top view and the side view you can see, which clearly says that it is a square, or the cross section area is a square. So, what you are trying to generate is a hollow part. The hollowness is brought in by the core, right. The core can be removed or it is expendable. So, you take the part out, you break it open, or you can try to have something to just release it out. Both are possible, right. So, this clearly says what are all, when you see the top view and the front view, you can see very clearly, visualize what are all the parts of a sand casting. Now, let us see how is this made. First, what we try to take is bottom board. So, this board is the bottom board here, right. This is drag. So, we try to keep the drag, the pattern we keep here. What is a pattern? From the pattern, what you get is the mold. So, we have a drag pattern, right, and then we try to have the drag portion, we keep the pattern, and then what we do is we pour the sand. Once we pour the sand completely, we try to inverse it, right. So, when we pour the sand, sand means it is not plain sand, sand with additives. The additives can be water, it can be clay, it can be any other binding, whatever it is, binding agent, all these things. So, it's got mixed and they try to dump it into the drag pattern. So, once it is done, it is also rammed, so that we get a solid consolidation of the sand. So, then it is flipped. So, the bottom here goes to the top here. So, you see the aligned pin, it goes to the top. Now, the pattern whatever you kept here is come to the top. Now, what we do is we keep the cope part on top of it. We lock the pin, and again what we do is we start filling the sand. When we fix the pattern, we also fix the sprue and the riser. Sprue is for pouring the hot metal, riser is for infeeding when the solidification happens. So, basically what happens, the metal flows from here, it goes into the pattern which we remove out, becomes the mold, and then it gets into the riser. While filling itself, it goes up to here. And then when it solidifies, the liquid metal starts coming down as and when there is a solidification in the pattern happening, right. So, now you can see here the pin, whatever is there, aligned pin, which is attached to a lug. So, it is locked, sand is poured, pattern is kept, and on top of a pattern you keep the riser and the sprue. So, this can be made out of wood, sprue and riser design pins can be made, or it can be made out of even thermocol, right. You pour it and then it goes, possible. You can pour it and then you can try to have the sprue, And later what happens, once the consolidation happens fully, we remove the sprue, we remove the riser out. So, the profile is retained, right. So, you see here pouring basin and the other things, parting, you see a parting line. Okay. Now, comes the question, how do I do the gate here and the runner here? So, as soon as you place the pattern here, before placing the pattern on the top, what we do is we try to make the profiles on the cope itself. So, then what we do is we remove the sprue out, we remove the riser out, and then we are also remove the pattern out, and then try to make the gate, and then we once again keep it together assembled, and then we start pouring it. So, pattern, sprue, riser, sand pour, everything is done. Then we, once every consolidation is done, again we try to remove the pattern, remove the riser, remove the sprue, and in the cope portion we try to make the gate and the runner. So, here you can see here skim bob is made. So, as and when the sprue comes, so we are trying to make a profile like this. So, that what happens, the liquid which comes here tries to fill, and then a uniform flowing happens to the runner. So, this is how a animation looks like that. So, you can see here how interestingly it is made. So, a liquid metal is poured. So, you can see the sprue is there, the riser is there. So, you remove the cope portion, you have the part. So, now whatever is the extra portion in the figure you see, those portions will be trimmed off. So, these portions will be trimmed off. So, you can see here whatever comes in these two portions, the component will be trimmed off. The sand casting is the most popular one and the simplest type of casting. It has been used for centuries. Even today, if you have a very large component, we always go for sand casting. Sand casting allows for small batches than permanent mold casting, and it is very reasonably cost when the batch size is small, plus when the component is very large. So, this now clearly tells you all the things: pouring basin, coming to gate, gate to runner, runner to the mold cavity. The liquid flows and then it tries to fill the riser. When the liquid flows in, the air gets through the vent, it tries to escape out. So, the core is used to give the internal geometry, right. And here you have a choke. So, the choke will try to retain the sand particles, whatever is, or you can have a filter here, which tries to filter out all the sand particles, allow the liquid to flow, and this skim bob is also used. These are all ceramically made. So, any sand particles will deposit here and only the liquid metal will flow. So, the steps involved in casting are core making, first step, this is core. Then we try to make pattern for the mold to be kept, we make a pattern. From the pattern you try to make a mold. So, in the mold you try to pour sand. So, pattern is kept, mold is made. Now, in the mold you try to melt in a crucible, you melt a raw material, then you pour into the mold, it is allowed to solidify and cool, it is removed from the sand mold and it is done cleaning and inspection or finishing, whatever is done is required, it is done, right. These are the steps typically involved in a sand casting. So, in sand casting steps, first is pattern making. Why do you need to make a pattern? We need to make a pattern because the pattern will be a negative of the mold. So, the patterns are the replica of the casting. So, if you take pattern, mold, final part, this and this will be similar. The mold will be negative of the pattern. So, the pattern are this replica of the casting. Take an example, I have a vessel like this, right. This is how the pattern is. Now, in this pattern, what do I do is I fill up liquid metal as a mold, right, and then when I take it out, I get the final part whatever I want. Patterns are manufactured from, it can be manufactured from wood, metal, wax, plaster of Paris. Wood and metal are generally preferred. Wood has only one issue. The issue is it can absorb water. So, it can get swollen up. So, if it is swollen up, so then the wood pattern will try to have a larger size of the mold, and wood has its own wear and tear attached to it. So, we replaced it with metal. It is expensive, and in metal, if you want to make intricate patterns, it is difficult. For example, if you want to make Ganesh, Lord Ganesh face, or if you want to make a human face, wherein which it is a scaled down version, very difficult. If you want to try to have a frog, a skin which is there, or a fish skin. So, it is very difficult to make in metal, it is easy to make in wood. So, we still go for wood, but metal, no absorption, no wear and tear, it can be used for mass production. Then wax, which is on the other side, where we make a wax. So, now this wax, liquid wax, you try to give a shape which is very easy, and then when the liquid, hot liquid metal is poured, the wax pattern will itself melt and go away, or you can try to have something like lost foam. The thermocol, you can have it, which it burns away and then goes on. You can also have plaster of Paris. Plaster of Paris are ceramic. It is easy to make because you can easily make by hand. So, for the preparation of various patterns, various tools and equipments are used. This is the original design, this is the pattern, this is the mold, this is the cast. You see here original design, pattern and cast will be the same. Mold will be the negative of it. So, once it is done, so the top portion, this can be riser or it can be a sprue, whatever. So, you trim it off and then this will be remelted and then this will be the final part. So, pattern, the casting process with some modification, and that is addition of pattern allowance, provision of core prints, elimination of fine details. These are some of the things which you should keep in mind when you are trying to make a pattern. Additional pattern allowance will be given. Why are we giving additional pattern allowance means, suppose if you have made a pattern like this, right, a sharp edged pattern. When you try to remove from the mold, sand mold, it is going to be, it will damage the surface. So, once it damages the surface, it is very difficult to remake the sharp edges. So, what we do is, we intentionally give a taper and we give slightly a larger allowance such that when the pattern is removed, it does not damage the mold. So, this one is called as the pattern allowance. Next one, if you want to have intricate shapes, then you will try to have a core. So, for holding the core, you will have a core print. And fine details have to be avoided. For example, if you want to take the skin, or the when you are trying to cast my hand and then you have a skin there, and then on the skin you have hair, these are very fine features. So, you generally try to avoid these features, right. These are some of the modifications we do. So, these are patterns with distortion allowance. The pattern, this is a distorted casting. So, because of the pattern mistake, you see the component is also done. So, this what we do is, we try to compensate and then we try to get the best out of it. So, these are some small machining allowance, because there can be sand which gets into the skin of the casting. So, there is a machining allowance to remove it to produce the part. Then there is a shrinkage allowance which is also there. Then there is a shake allowance. So, these are some of the allowances which are given to the pattern. Shrinkage is all metals shrink when cooling except bismuth. So, bismuth have a negative expansion. This may be due to the interatomic vibration amplified by the increase in the temperature. So, they always are volume is big. So, as and when it is solidified, it shrinks. So, that is called as shrinkage allowance. There can be two types of shrinkage. One is liquid shrinkage, the other one is solid shrinkage. Reduction in the volume when the metal changes from liquid to solid at a solidus temperature is called as liquid shrinkage. The reduction in the volume when the metal loses temperature in the solid state is called as solid shrinkage. There are two types of shrinkage, liquidus shrinkage, solidus shrinkage. Then why? You go back to this diagram, what we studied. This is temperature and this is time. Right? You also have a unit volume. Actual volume of the shrinkage depends on the composition of the alloy, mold material and the complex pattern, complex design of the pattern. So, there is also a machining allowance which is given. So, the machining allowance is you have now made a taper in the pattern. So, in the mold you will get a taper. Now, in reality it might be a straight part. So, we have to remove this material. Okay. When we have to remove this material, we should also have some holding. So, holding of this part. So, what we do is those things are considered and given in the pattern itself. So, once the mold is done, the casting is done, we try to remove all the extra one and we also try to remove all the taper such that it meets to the requirements. Extra material is provided which is to be machined or cleaned for good surface finish and dimensional accuracy. Depending upon the casting material, dimension, finish required and the complexity of the surface, 2 to 20 millimeter is given as machining allowance in the pattern itself. The draft allowance which I have told you, this is the actual casting, but I cannot get the actual pattern like this, I do a taper. So, that is called as draft allowance. This one is called as a draft angle. The vertical face of a pattern are to be made taper to reduce the chance of damage to the mold cavity. It varies with the complexity of the job. Inner details require more allowance than outer. So, this is outer. So, if I have a hole, this is inner details. Okay. So, this portion if I try to take, that is called as outer details. This allowance is more for hand molding rather than machine molding. Shake allowance, see draft allowance is removing, shake allowance is which is generally given, we shake and then we take the part out. So, the shake allowance compensates for the dimensional change due to the mold movement or vibration due to casting. See, when you try to remove, we shake and then remove, right. So, applied to dimensions parallel to the parting plane. Parting plane is you have cope, you have drag, this is the parting plane. Identifying a parting plane for the part is very difficult because and it is very crucial. Moment you have decided your parting plane, the overall strength of the part depends on the parting plane. Okay. Applied to the dimensions parallel to the parting plane to account for shrinkage and distortion. It ensures the final casting retains its intended shape and size after cooling. We give a shake allowance. So, what are all the allowance till now we have discussed? Shake allowance, draft allowance, machining allowance, and then we have talked about shrinkage allowance. So, 4 allowances we have talked and all these things are given to the pattern such that the component whatever, the cast whatever you make is good, right. So, what does it mean is the mold size will be slightly larger than the expected one, that is what you have to understand. And there can be taper, there can be sharp edges, there can be a flat projection, all these things will be removed when you make the final part. So, the distortion allowance occurs when the different cross sections of the casting cool at varying rates. For example, if I have something like this, right. So, here there are different cross sections. So, at different cross sections, now what is happening? The solidification happens at different periods of time. Because of this, it introduces a residual stress in the component. because of the residual stress which is induced, you will always get a distorted component. So, in order to remove this, we give a distortion allowance. Distortion allowance occurs when different sections of the casting cools at varying rates, causing internal stresses and change in shape. So, this is what is needed. The surface area, we play with the volume and surface area, it gets distorted like this or like this. The camber allowance is applied by slightly oversizing the pattern to counteract the cooling distortion. So, this is the required shape of the casting, this is the distorted casting, and this is the camber pattern. So, now I can get this. Camber allowance is applied by slightly oversizing the pattern to make sure that while cooling it tries to give you the best. The patterns are designed with inward convergence and adjustments to prevent distortion and ensure accurate final dimensions. So, this we have seen in detail. Just quick brush through: mold and core making. Both the mold cavity by using pattern and using core for making the hollow patterns in the cast, melting and casting. The melt the metal in the furnace and pour it in the mold cavity, wait until it solidifies. As the casting gets solidifies, remove the cast part from the sand. Cleaning of casting: remove the casting from the sand, cut the runner, riser, also trim the flash appears at the parting line and other places. Testing of casting is done for various defects. So, advantage of sand casting we have seen: wide range of metals can be sand casted. The shape and size plays an important role. It is a low cost. When there are large sizes, sand casting is the only option. When we talk about the disadvantages, sand casting leads to poor surface finish and it has wider tolerance. Now, let us try to see the important sand casting terms. Mold: a hollow structure created using a pattern is a mold. It is filled with molten material to form the casting once the material solidifies. It makes the mold. The grains of the sand are held together by a mixture of water and bonding clay. A typical mixture of the volume will be 90% sand, 3% water and 7% clay. The molds in sand casting are expendable, they break and throw it. Permanent molds are reusable type, wherein which they are made out of metals, used to produce multiple castings of the same size. Expendable molds: the mold is prepared every time and the sand is destroyed. Maybe you do a preparation and the sand can be reutilized. There is open mold and there is a closed mold. Open mold: they are simple, inexpensive, made of sand or basic material. The liquid metal is poured directly into the cavity, making sure the suitable for low precision parts, open mold, but with less control over the metal flow, leading to a higher risk of defects. Open mold. So, this is a closed mold. If you see here, this is a closed mold. Closed mold made of metal, ceramic or alloy features a gating system for controlled metal flow. It offers high precision, better dimensional accuracy and surface finish. It is ideal for complex shapes despite their higher cost and complexity. This is the open mold. So, you just pour it. For example, if you want to make, you have a liquid metal and you want to make ingots, then we just pour and then we try to make it like ingots, right. For example, you think of sugarcane jaggery getting formed. The sugarcane juice is heated, the viscosity is changed, it is poured into a die and then they take the jaggery block out, right. Today you get a small injected jaggery also. So, those things are called as closed die. So, this is open and this is only as a ingot. Most of the time this will never be used for the final output. If you want to think of an analogy which you regularly see at home, the ice cubes which you extract from the ice tray, they are all open mold. There is no intricate shape, nothing. It is a taper given. So, you just turn it and then do it. So, if you see the ice cubes, it will always be tapered. You will have ice cube like this, always. See here. So, if you see this today, you will understand, right. The other way around is you put it inside, you have a precise shape. So, you get it, that is closed. We always talk more about closed molding, where in which here it is going to a final part. Core, these are the most important one. These cores, there can be horizontal core, there can be vertical core, there can be a balanced core, there can be a drop core. There are multiple types, but primarily core are used to give hollow features in the final part. A separate piece used to form a hollow or an internal feature of the casting is done by core. It is placed inside the mold cavity and is usually made out of sand, metal or ceramic. Yeah, it can be sand, metal, wood also can be thought of. Sand is most probably used. Gating system. So, what is part of the gating system? So, pouring basin, sprue is done. So, from here the sprue is attached to a well. From here there is a runner, and then at the entry to the mold you can have a gate. So, this is the gate. So, gate is like our gate at the entrance of our house, gate, where in which it enters the mold. In this example, you have given a blind riser, right. A system of channel, sprue, runner, gate designed to control the flow of the molten metal into the mold cavity is the gating design. So, gate, runner, you should understand runner also you will try to have taper because the continuity has to be maintained. It ensures uniform filling without any defects. So, this is top riser, pouring basin, this is a runner, and at the entry of the mold it is called as the gate. The gating design ensures proper metal distribution, preventing temperature loss, turbulent gas entrapment, slag formation. Slow pouring may lead to early solidification before the cavity is filled. Fast pouring can erode the metal. So, that is why we were always talking about the pouring basin, a taper, a well, because from here immediately you can try to have a, like from here you can immediately change the direction. But when you change the direction, there can be a possibility that there can be vena contracta effect and then there can be solidification. So, what we do is we try to create a well and then the liquid metal comes here and slowly it starts filling it. So, fast pouring can erode the mold. Gating design depends on the metal and its composition such as aluminum susceptible to oxidation. So, all these things are very important when we start doing a gating design. Gating system, there can be three types of gating system. One is called as vertical gating system, two is called as bottom gating system, and the third one is called as the horizontal gating system. When we talk about the gating system, gating design means sprue is also included, sprue, runner and gate, right. So, if you have an open gating system, you have a pouring basin, then you have a sprue. So, here whatever is there, it is at atmospheric pressure. At the change of where the sprue starts, it will be 2, and at the end of the sprue, you will have point number 3. So, the heights are defined. So, it is HC is the height of the pouring basin, then H2 is the sprue height, then HE is a combination of HC plus H2, and from the point number 3 it is exposed to a mold, so open to the atmosphere, right. It is like a open mold. So, when we talk about a closed mold, this is called as HG, which is H2, and this is HC, right, and then this is the mold height, and this when the when the liquid is flowing, the top level of the molten metal is this height is called as H. Okay, this is for a bottom gating. Bottom gating system always gives you a very good result. So, vertical gating, molten metal is poured vertically into the mold using atmospheric pressure at the base to guide it. Ideally, for molds require high pouring rates. Bottom gating, metal is poured from the top but fills from the bottom of the mold, minimizing the oxidation and splashing for a clean flow and improved quality. Horizontal gating enhances the bottom gating with horizontal channels to improve the metal distribution, reducing the turbulence and preventing defects. So, bottom it goes up and horizontal is like this. Top is from the top, right? Vertical gating system. So, for a vertical gating system, let us now try to find out what will be the velocity with which it is done. So, we always have to use two simple equations, Bernoulli's equation and continuum equation. So, the Bernoulli's equation is written as H1 plus P1 rho g plus V1 square by 2g plus F1 is equal to H3 plus P3 rho g V3 square by 2g and F3. Now, in the vertical, P1 and P3 and the level 1 is maintained constant. So, P1, P3 goes away. V1 is the atmospheric pressure. So, that is also gone. So, now what you have is, we will have H1 plus F1 equal to H3 plus you will have the other term plus F3, right. So, the energy balance between point 1 and point 3, if you do, what you get finally will be 2 GH, you will get GHT is equal to V3 square by 2. So, velocity at the point 3 is going to be root 2 GH. So, here V3 is referred as the velocity of the sprue base or the say gating Vg. The continuum equation Q will be A1 V1 equal to A3 V3. So, now substituting all, we try to get the mold filling time will be V by Ag into V3. The metal flow into the sprue opening, it increases the velocity and hence the cross section area of the channel must be reduced. So, this is A1 V1 equal to A2 V3. The velocity of the flow molten metal increases towards the base of the sprue. The air can be aspirated into the liquid and taken into the mold cavity. So, you should be very careful. So, you can't go at infinitely very high velocities. Please be careful. To prevent this condition, the sprue is designed with a taper, so that the volume flow rate Q equal to AV remains the same at the top and the bottom of the sprue. Top and the bottom of the sprue is the same. So, we try to have A1 V1 equal to A3 V3, right. So, the time for filling is nothing but V by Q. Q is the flow rate. So, flow rate is done by the velocity, right. So, the cross section area of the gating system is Vg, the velocity is V3 at the end of the sprue, V is the volume of the mold. So, we can try to find out mold filling time for a vertical gating system is going to be this. Now, let us try to take the option of bottom gating system. In bottom gating system, the assumption is this is the minimum time required to fill the mold cavity. Hence, the analysis we ignore friction losses and also possible constriction of the flow in the gating system. The mold filling time can be calculated by the same Bernoulli's equation and the continuum equation and all. So, it can be written as Vg equal to V3, which is 2g Ht minus H. So, this is H and this is Ht, Ht minus H, right. So, applying Bernoulli's equation between the point 1, 3 and between 3 and 4 to modify the V3 in the equation in the previous gating. So, we try to get this. So, this Ht minus H is effective height, because this can be increasing, this can be decreasing. Between 3 and 4, we assume V4 is very small. All kinetic energy at 3 is lost after the liquid metal enters the flow. So, these two are the assumptions. Based on the assumptions, we try to get the velocity at gate. So, assuming in the mold the height moves up by delta h. So, this is one which moves a height of delta h. Okay. Assuming in the mold the height moves by delta h in a time delta t, AM and AG are mold area and the area gate. So, AM dH is equal to AG Vg into dt. Now, what we do is we combine the two equation and we get this form. So, now we integrated between 0 to HM and we 0 to TF mold filling time. So, this can be rewritten, and after solving the equation, it can be mold filling time will be area of the mold by area of the gate 1 by 2 2g 2 into root ht. What is root ht? Root ht is the total height, right, from 1 to 3 minus root of ht minus hm. Where is hm? Hm is the mold height minus ht. So, with this we will try to get the mold filling time for bottom gating system. In the top gating system, it is mold filling time is straight, and in the bottom filling time, it is to be derived and taken. So, you please work it out. We will have 1 or 2 problem sessions, where in which in detail we will step by step we will try to show. Continuing with the important terms of design gating system, aspiration effect. This is very important. Aspiration effect, where the gas enters from baking of organic compounds present in the mold into the molten metal stream. So, what happens is the air enters from the walls. This is the mold. From the wall, the air enters into the mold where there is molten metal. So, you have molten metal and this air goes there. So, when the air goes there, it is going to lead into defects, which will produce porous casting. Pressure anywhere in the liquid stream should not become negative. So, what happens when you remember A1 V1 equal to A2 V2 we were seeing. V2 is the velocity at the gate and other things. Make sure this velocity is always high, it does not go to negative. Moment there is a negative thing, it will start sucking back. Moment it suck back, it will not produce a solid part. Pouring basin, we have gone through it enough. This reduces the eroding force of the liquid metal poured from the furnace. This also maintains a constant pouring head. So, one is the liquid should not flow out, then it should also have a constant head. Experience show that the pouring basin depth of 2.5 times the sprue entrance diameter is enough for smooth metal flow. So, they have also come with some empirical numbers 2.5 times. The radius 25 R is good for smooth entrance sprue. If you look here, this is 2.5 D and this is 1 D and here is the radius. So, the metal gets filled here and then from here it goes into this. So, now it will be a smooth flow whatever you want. So, when we do that, there is a possibility it can have oxides or it can have soil erosion something. So, we always put a strain core. Strain core is there. So, liquid comes and then it can go like this. You can also have a delay stream. So, this strain core and delay stream have similar functions. The items provided in the gating system to avoid impurities and turbulence, these are used. So, the important terminologies here are delay screen. It is a small piece of perforated screen placed on the top of the sprue. Delays screen. Strainer core, it is a ceramic coated screen with many small holes and is used for same purpose for stopping the small pieces. Splash core. Splash core provides splash core splashing. Splash core provides at the end of the sprue length, which reduces the eroding force of the liquid metal. We also have skim bob. Skim bob are used to trap lighter and heavier impurities in the horizontal flow. So, all these things are doing a similar function like bringing in smooth flow, stopping unwanted elements to enter inside, and it also tries to have a uniform flow. So, there is something called as a gating ratio. The gating ratio is always written as sprue area is to runner area is to gate area. Gating system is of two types: non-pressurized gating system and pressurized gating system. In the non-pressurized gating system, it has a choke at the bottom of a sprue base and has total runner area and gate area higher than the sprue. I repeat, it has a choke at the bottom of the sprue. What is sprue? Bottom of the sprue base, and has the total runner area and the gate area higher than the sprue area. So, no pressure is present in the system, hence no turbulence. So, the chance of air aspiration are possible. Generally, this non-pressurized is used for aluminum and magnesium alloys. The recommended ratio is sprue 1, runner 4 and gating area 4. Pressurized system. Here the gate area is smallest, the gate area is largest, the gate area is smallest, thus maintaining back pressure throughout the gating system. This back pressure generates turbulence and thereby minimizing the air aspiration even when the straight sprue is used. Very important point. The back pressure generated during turbulence, thereby minimizing the air aspiration. Air aspiration, you remember, we have seen, right? So, here there will be a curing and here there is, these are all metal and this is a sprue, air aspiration. Even when the straight sprue is used, not good for light alloys, pressurized one, but good for ferrous casting, die casting, right? Pressure die casting. Suitable for ferrous metals like steel, the gating ratio is 1:2:1. So, here we have presented all different gating design ratios for aluminum, aluminum and bronze, brass, copper, ductile iron and grey cast iron. We can also see for magnesium, malleable iron and steel. So, you can have pressurized gating system or non-pressurized gating system. Risers. Riser is a reservoir connected to the mold cavity. Serves as a source of extra molten metal to compensate shrinkage during solidification. You can have a straight riser, you can have a taper riser, you can have a step riser you want. The shape can be any. You can also have something like a mushroom type riser, depending upon your requirements, right. So, you can also have blind risers, right. So, straight riser, taper riser and step riser. Predominantly what we use is taper riser. So, there is something called as a draft angle. A slight taper added to a vertical surface of the pattern is called the draft. It facilitates the removal from the mold without damaging the cavity. So, you can have poor ideal draft you can have. This is positive draft, this is negative draft. We avoid negative draft. Draft means it is a small taper you give such that the part can be removed from the mold. It facilitates the removal from the mold without damaging the cavity. So, there are vents, these are all vent holes which are there. These are small openings in the mold that allows trapped air and gases to escape, ensures the molten material fills the cavity completely. So, you can have these are riser locations, these are small vent holes which are there, vent holes, right, riser locations. When we talk about a pouring cup will always be something like a funnel shape. The funnel shaped structure at the top of the gating system that minimizes the turbulence and directs the mold into the sprue. So, you have liquid height in the sprue cup, which is HC, this is HC which you have already seen, and the area of the runner is AC. So, the input flow happens and then you have the area of the runner is AG at the gate, right. So, maximum radius will be RC max and the height will be HC max, maximum height, minimum radius and maximum radius for the pouring cup. Parting line, we have seen the parting line, one of the most toughest and a difficult task is identifying a parting line for any given component. For any given component, identifying the parting line. The parting line dictates the mechanical behavior. So, you can make the component like this, you can make the component like this, you can make the component like this, like this. These are all parting lines. It is left to you to decide. So, there are softwares which can help you in identifying the parting line, because the parting line will try to divide the cope and drag part. Okay. So, in sand casting cope and drag part, when you go to metal casting, you can also have which can move like this horizontal. Here it is vertical, there it can move horizontal. The line or a plane where two halves of the mold meet is called as parting line. It is often visible, So, when you see even your pencil box, you see there, you will see a straight line going on. If you see sometimes a bottle, plastic bottle, you see a parting line. When you see a cast piece like a bell, you can see a straight line. So, those are all parting lines. It is often visible in the finished casting. So, we already discussed about chills. Metal inserts placed in the mold to increase the cooling rate in a specific region is chill. So, this is the mold, this is the casting, this is chill, this is the mold. You can have casting, you can have mold, you can have chill, and then you can have this. So, it is touching chill, casting is touching chill. This casting, the chill is non-touching the casting, and here you can have standard and deformable chills. So, the chill sand, deformable chills. It improves the mechanical property of the casting. So, these are all shaped chills, these are all standard chills which are available. Chills are nothing but something like a building block, like your jigsaw puzzle, you have a building block. With this building block, you can try to make multiple chills to join together to meet out to the requirements. So, with this, I am sure you will now appreciate and understand sand casting. How is a sand casting made? In sand casting, what are all the parts? Cope, drag, mold, core, core print, sprue, riser, vent. These are the things we saw. We saw pattern, what are all the allowances? In pattern, you have shake allowance, machining allowance, taper allowance, distortion allowance. All these things are given such that you always try to get a solid part. And while going through the discussion, we also saw what is the pouring time when we use a top gating system and a bottom gating system. I am sure you will now have a good understanding about sand casting and the processes. These are the references which we have used in this lecture. Thank you very much.